All right, so this video will be about the stress intensity factor, which, as I talked about in the last one, is the way that you want to think about fracture mechanics for most of the practical stuff. It's all geometric, so you can put it in nice tables. And so where this comes from, because I think some of the equations can be a little bit hard. Basically, you have, like I said in the last one, you have a track like this, and the track is moving by a tiny distance, dA. And in this case, what people were trying to do back in like the 30s and 40s was find the stress field near the track tip right here at A. And so this first person, Westergaard, found one that was exact, but it only worked along this line. So where y equals 0, he had no idea about what the stress was like at the top or the bottom. And so what Irwin did was he found an approximation that worked when you're very close to the track tip. It doesn't work very well very far from the track tip, but that doesn't actually matter for our purposes because we only care about the intensity near the track tip. So this is what like the actual field looks like. And when you do it along the line where theta is equal to 0, which is the one near the track tip, you get basically our stress intensity factor. You get like this right here. So this is the one we're dealing with most of the time in class, and this is our K1. And so when you rearrange it a little bit and use R is equal to like 2 times A, you get our stress intensity right here. Okay, now moving on. So that's just where it comes from. You don't have to worry about that so much. All you really need to know is the K1 equals F sigma root pi A. Like if you know that, you're pretty much good. Now this one will be about track tip plasticity. So remember in metals and other things, when you're near the track tip, the stress concentration from the track causes plastic yield near the track. And so we have like different ways of approximating the plastic zone. And that zone is what gives metals a lot of their toughness. Like the fact that when you have that when you have that stress strain curve, remember the toughness is the area underneath this curve. And so that's where a lot of that comes from, is because energy is being dissipated by plasticity near the track tip. So the way to like sort of, we can approximately look at the plastic zone, we take that equation that we had before on the last slide, where the yield stress, and you plug in the yield stress into this, where it's equal to K, this will be K1 over root 2 pi R Y. And she does this in some of the class notes. And basically, in the case of plane stress, you get one formula, and plane strain, you get another one. And you can see here the plane strain is going to be the better approximation because it's assuming the worst case scenario. And so that's where usually our K1C comes from, is from the plane strain situation. So this is all an approximation saying that the plastic zone is circular. But if you take that track tip stress field on the last slide and you take each of the components of stress and you find the von Mises yield, then you get this real surface that looks kind of like a kidney bean. And so this one is also in the class notes. And basically what it's showing here is that near the track tip, you have plane strain deep into the material, and then as you get closer to the surface, you have plane stress. So I think this figure is really nice because it makes it easier to see. It's like showing that in this case, B is the thickness of the material. And so very far in here near the center, you have a smaller plane strain. And then right out here near the edges, you have plane stress. So if you had like an infinitely thick beam, you'd basically be looking at plane strain everywhere. So hopefully that's helpful. I'll do a quick example problem. This one will help you to kind of look at where to look in the data book. So when you have a problem like this, laser-based additive manufacturing with powder beds, okay. Penny-shaped flaws. When you see penny-shaped, circle. And so consider the printing of a 1 diameter cylindrical rod that contains a circle defect that's 300 microns. At what load will this rod fail? Okay, so first things you do here, you just assume for a second there's no defect and you see if it yields, and you check the tensile strength. And we're just going to move on from those. Those are pretty simple. And then finally, you also have the fracture toughness. Okay, so now we want to go to our K1. That's our K1C right here, our fracture toughness. And megapascals root meters. So K1C equals 100 megapascal root meters. Okay, so now we need to check, or we need to find K1. And so what we're going to need is we're going to need this shape factor, F, and then we need to find our stress, which in this case is really simple because it's just, I'm going to turn our other circle into this. It's a cylindrical rod. So you just need the area of the cylinder and the force at the end. And then root pi a. Yes. Okay. So we're just going to calculate this and see if it exceeds K1C. I wrote over this. So basically, the first idea is if I give you all of these pages, which are all from our data book for the midterm, it's which page would you want to use for this situation. So you have one that has this cracked shafts, this one that has circular cracks, edge cracked beams, and edge cracked plates. And there's also some center cracks in here. And so I'd recommend taking a second and pausing this video and figuring out which page you think it is. And if you're done with that, it's the circular cracked one. And now the next question is, out of these 4 geometries that are here, which one do you think is the right one for this problem? So recommend, again, pausing it again. And if we're through that, it's actually going to be A, because we're looking at a crack that's deep into the material. All 3 of these are different types of edge cracks. So this is an edge crack at a rectangular surface. This is an edge crack at the intersection of 2 rectangles, and then this one is an edge crack in a cylinder. So we actually want case A here. And so it's saying the factor F when A is within, like these, when A is A over T and A over B is 0, less than 0.5, then this F is plus or minus 10% accurate is basically what it's saying. So this fracture stuff, it's all about approximations like this. But we can just grab this 2 over pi, and we also over here have the tensile stress, but this isn't actually anything interesting, P over 4BT. It has 2B is the length of this, and 2T is the length of this. So it's just saying force divided by area, just the classic thing. So now we have K1 equals, and then A is the radius of the crack, which in this case will be half of the diameter. So we have F is 2 over pi, that's F. We have the stress is the load, which we don't know, load over the area, which in this case is just the diameter, the area of the circle. So 1/2 pi diameter over 2 squared. And then we have the root pi a. And then A, in this case, is also diameter over 2. Because look at this figure if you don't see that for a second. And then finally, so this, we know what this one is. This is our stress. This is root pi a. And the last thing is now we want to say, what we're solving for here is the load. So we just say, what's K1 equals K1C. And then when you do that, you can solve for P. I'm not going to go through all the actual numbers because I don't want this video to be too long. But hopefully that's helpful. If you can get to this point, if you can read the tables correctly and you can plug it into the equation, then you are good to go. So there we go.